So back when you guys were in geometry or in pre-cal last year, you probably talked about a few different types of lines. One is the secant line and one is the tangent line. I drew a little representation here on the right, but a secant line is a line that intersects a curve or a circle in exactly two places. A tangent line, however, is one that only intersects at one point. Now, that has been kind of the working definition that you guys used in the past. But I want to make it known that a tangent, a lot of times we think that it's maybe something that only intersects the curve at exactly one point or touches the graph at exactly one point. Now, this could be true when we're dealing with something like a circle or a parabola, but when I start looking at higher order polynomials, sometimes I see a tangent line that touches or intersects the curve at multiple points. So let's refine our definition of a tangent and say that a tangent to a curve at a point is a line that best models or approximates the behavior at a curve at that point. Now, this is don't confuse these two things. This tangent line is only tangent to point P on this curve. It is not tangent to point Q, even though it intersects point Q. So let's talk about this whole idea of a tangent line and what it represents. A tangent line truly represents the instantaneous rate of change at that particular point on the curve. So for example, if I made up a new point and I called this point S, and I were to say, what's happening here? Well, I know that we are increasing at a pretty high rate, so my line tangent to my graph would probably look something like that, a pretty high positive slope. On this turnaround, let's call this point T, we would have a flat tangent because right here we are neither increasing or decreasing. It is down at that dip for a second before it changes from decreasing to increasing. So this whole idea of a tangent line, what it truly does is it helps us find the slope of a curve at a point. Also note that the slope of a curve is a specified point, and we'll call the slope of the tangent line or instantaneous rate of change or derivative. They are all synonymous. Slope of a curve, slope of the tangent line, instantaneous rate of change, or the derivative. We're going to talk about that a little bit in detail later, but you might see this instantaneous rate of change written as ROC, and whenever you see that, just know that that means instantaneous rate of change for future reference. The most important thing to note here is that the tangent to a curve at any point is unique. A function f that has a defined slope at x equals a has two things in common with its tangent at x equals a. So let's take that through really fast here. What we're saying is we're given a value for an unknown, and we're saying this value, we don't know what it is, but we're calling it a. The output of this function, if we were in terms of f of x, would be if you plugged in a to the function f, that would give you your y value. So I want to go over a little hypothetical really fast, and then we're going to dig into a little bit more meatier problems and hopefully help you understand this. Let's just say hypothetically that this line, the equation of this tangent line, so here's our tangent line, is going to be y equals 2/3 x plus 4. Just making that up. If this equation of the line is 2/3 x plus 4, we're saying that the instantaneous slope, or the slope at that point, is 2/3, so that we could say that the derivative, or the instantaneous rate of change happening at point A, is 2/3. That 2/3 is that instantaneous rate of change. Instantaneous rate of change is synonymous with the derivative, so I can also say f prime of A is 2/3, because I'm saying that the instantaneous rate of change, that prime rate of change at A, is 2/3. Now, this can change regardless of where that tangent line is on the curve. For example, my earlier graph, the tangent, or g prime of t, would actually be 0 because we're flat. At S, that would be a really high positive value because my slope is increasing at a rapid rate. And if I were to actually draw the point of tangency at, let's say, point Q, the line of tangency, it would be a negative, or g prime of q would be a negative number. The other key thing to note is that any function with a defined slope at a specific point will have one and only one tangent line at that point. I cannot say that this point at point A, I cannot say that any other thing is happening about what's happening at point A than this one line. You cannot draw multiple lines and say, well, maybe one of them is correct. There's exactly one correct answer, or maybe multiple of them are correct. That's not true. Only one correct answer of what's happening. Now, when we think about like, okay, how do I find this instantaneous rate of change? This was totally a guess. So how do I figure out like what is actually happening here? We're going to take some concepts that you guys have been talking about since Algebra 1, so a very long time, and we're actually going to take those concepts and start manipulating them even further into some calculus level stuff. So first off, we do know the average rate of change. You guys have done this for forever. y2 minus y1 over x2 minus x1, or rise over run, delta y over delta x. This is going to be the value of the slope of the secant line. So the secant line, or the average rate of change, is what's happening between these 2 points. Now when I'm plugging this in, let's say the point P, let's call this A and f of A. Remember that f of A is a similar thing of saying like a fancy version of y, and A is a fancy version of x. The same thing here for point Q, another fancy version of x and y. If our input is B, our output is the function with regards to B. So really what I'm just saying here is y2 minus y1 over x2 minus x1. I want for you to pause the video for a second and find the average rate of change of this function over the interval. So know that we'll need two things. We need f of 1 and we need f of 3. And then we need to plug it into that formula and say what is f of 3 minus f of 1 over 3 minus 1. When I get this math done, so I plug in a 1 and I plug in a 3, my outputs are -2 and 18 respectively. So I just plug those into the formula and we get the average rate of change is 10. So let's take this idea and start thinking about this average rate of change and apply it. Like, how can I use my knowledge of average rate of change and convert this knowledge into instantaneous rate of change? So in my brain, I start thinking and I say, okay, so let's maybe try to make this into 2 points. But if these 2 points lie exactly here, so let's say that I also have B and f of B, and f of B and f of A and B are the exact same. When I use these, we only have a single point, so my average rate of change formula will actually produce an indeterminate form, and it's going to be useless. So let's do plan B. Plan B is let's choose a second point that's super close to our point of tangency, and we can call it point Q. So what I mean by that is, let's say that we have points P and points Q. And to get this as accurate as possible, and notice that this is very, very zoomed in. To get this as accurate as possible, we want to only add a little bit amount to every single x value of point P. So if this were like a real value, right, like an example of this could be that your point P, let's call this, let's say that A is 2 and f of A is going to be 1.5. What I'm saying here is that I want to add as little as possible, and let's call that h. So adding as little as possible, so point Q would be 2 plus something very small, and then that output plus something v small. We're going to call that very small number h here. So we're saying that point Q is A, but only just a tiny bit more added. Now the whole goal is for h to be a super small value, but not directly 0, because if we move Q directly on top of point P, then h goes to 0. So now I'm going to rewrite my average rate of change formula, and I'm going to use these two variables as my y2, y1, or my f of a and my f of b. So let's get this written down here. The average rate of change in this scenario is going to be that second y2, so that f of a plus h minus y1, which is f of a, over x2, which in this case is a plus h, minus a. I can do a little bit of simplification in the denominator by removing those parentheses. And I'm just going to rewrite this as f of a plus h minus f of a. I notice that these a's cancel out, so this is all over h. So remember that what we're trying to do is we're not trying to find the average rate of change or the secant line. We're trying to find the tangent line or the instantaneous rate of change. So the slope of the curve of the point, we're trying to find that ROC, or that instantaneous rate of change. And so even though the slope is always changing, we know that slope of any line is constant, even our tangent line. So what we're going to do is we're going to start applying that limit rule to our rate of change. Because what we're doing to change this average rate of change into instantaneous rate of change, we need to apply a little bit of math notation. So what I'm going to say here is I'm going to say I can call the instantaneous rate of change, or the derivative of a function. I can say that m value, right, that rate of change, is going to be equivalent to this equation that we wrote earlier, but I'm going to add one key piece here. I'm going to add the limit as h approaches 0. I want for you to pause and think about why I added that, and then we'll go over it. Going back to that original example, what we want to make this as accurate as possible, the reason we add that limit is because we want this distance to be getting as close to 0 as possible. So my whole goal is that when I look at my formula, what I'm doing with that h value, it can't ever be 0 exactly, because then I'd be dividing by 0 and getting that indeterminate or undefined version. But I want it to be as close to 0 as possible, because at that point, if I am so close to 0, I can essentially claim that my average rate of change is essentially equivalent to my instantaneous rate of change. So going back here, we're saying that if I add this piece about the limit as h approaches 0, this average rate of change formula now turns into the instantaneous rate of change derivative, or the slope of the tangent. So essentially what we're trying to do with this tangent line is get it so close, so pull these points so close together that we get a really good idea of what that instantaneous rate of change is on that exact point. So let's practice. It says given the function f of x equals x squared, use the difference quotient, which is what we just calculated, to find the slope of the curve at the point 3, 9. So guys, key word, every time I see things like this, I'm going to write this formula down. I'm going to say the difference quotient is, let's get that copied to make sure we're perfect. We're going to say the limit as x approaches 0 of f of a plus h squared minus x squared all over h. And I want to apologize here. I just realized, fix this really fast. Fix. I just realized that I went one step ahead of my brain. So let's take a step back. The difference quotient is the limit as f of x approaches 0 of f of h approaches 0, f of a plus h minus f of a over h. So then in context, here's where I was at. We're going to say m equals the limit as h approaches 0 of, we're going to plug in that function. So that function here is going to be a plus h squared minus f of a. So let's see what's happening here in this function. Our function is x squared. So I'm just plugging in this a plus h in for my x value. So my function is whatever input squared. We're saying our input is going to be a plus h, and our second input is going to be a. So we have a plus h squared minus x squared over, a squared over h. And then we're going to keep on working. It's important that you're saying the limit as h approaches 0, because if I'm not saying that I'm trying to shrink this distance, then we're not actually finding the slope. We're finding the average rate of change between 2 points. And I'm wanting to make it known that I'm turning that average rate of change into an instantaneous rate of change. So let's expand this binomial right here. When I do a plus h squared, I should get a squared plus 2ah plus h squared. We have that minus a squared all over h. Now I'm going to cancel. I can take one h out of all these terms, and we should be left with the limit as h approaches 0 of 2a plus h. Now, I know that my h value is approaching 0, so I can actually start doing some direct substitution. So I'm going to say here, m is now going to equal, because I'm going to get rid of that approaching 0, 2a. Now, let's go back to what we're saying here. Remember, our a value is just another variation of x. And what we're looking at is our x point in this scenario is going to be 3. So we can rewrite this as we're going at a equals 3. So if I were to plug that in or substitute, I would get that my slope is going to be 6. So I can summarize here the slope of the curve at 3, 9 is 6. And we just use that difference quotient to change that average rate of change into instantaneous rate of change by moving the distance between those 2 points so close to 0 that it was negligible. The last thing I'm going to point out before we kind of wrap it up here is that what we just did here for this equation, this works for any value on x squared. So this equation we could use to find the derivative of any a value. So it can be used to find any f prime of a. So if I ask you on this guy, if I said, okay, well, for the same equation, what's the instantaneous rate of change when x equals 100? I could just plug 100 into that value there, and I would say, oh, the instantaneous rate of change is 200. Last but not least part right here is we are going to be writing equations of tangent lines. So remember that when we write an equation of a tangent line, what we're doing is we require a point and a slope. We're going to be using point-slope form a lot in calculus. I'm actually going to scratch that out because that's not what you usually see. You usually see the form y minus y1. It's an equivalent form, but this will be the general. And it says now that you know what the slope is, let's actually get an equation of the tangent line. So I found the slope earlier. I know that my slope is 6, and I know what my point is. So my x1 is going to be 3, and my y1 is going to be 9. So now we are just plugging in. And the best thing about calculus and the AP test is you do not have to simplify. So as long as you get those two things plugged in, you are good to go. So I'm going to say here, y minus 9 equals 6 times x minus 3, because all I did was I substituted all these values here. And once you were done, you're good to go. Box it. Don't worry about simplifying.